All right, so a little more matrix algebra. We talked today quite a bit about some of this. So remember, any matrix, if you can add them, of course, they have to have the same dimensions. They don't have to be square, they have to be the same dimension. So a plus b is b plus a. The commutative property is true, of course. So is associative for addition. Okay. I don't think that surprises anyone. Of course, it does have the additive identity. This is a zero matrix. So if you add a zero matrix to an A matrix, you just get the A matrix back again. It has the additive inverse. That is the negative, of course, of everything. Gives you the zero matrix. Duh. Now, like, sometimes you think that that's kind of stupid. Why do we bother going through that? Well, it matters. Sometimes it's going to come up into play in a little bit. So if this is a scalar, these are matrices. You take the scalar times the first one plus the scalar times the second one. It's the same thing. It looks like distributive property because, well, it is. Of course, you could have two scalars as well. You could have two scalars added together and then multiply them times a matrix. Same thing. Nothing too exciting there. And then, of course, you can do multiplication. Now, multiplication is commutative, or associative rather, if you're talking about a matrix and two scalars. Okay, you can do that first, whatever makes you happy. And then, of course, I is the identity matrix. Remember, the identity matrix is always ones on the diagonal and then zeros everywhere else. And it's always a square matrix. It's always n by n. So that times a is always a. Okay? So those are some of the big topics. We've talked about some of them. I think I've kind of hinted at them. I don't think I've gone through every single one of them at that point. We mentioned the other day somewhere, I think, that A transpose, if you have A, if A was this guy, then A transpose, instead of being a 2 by 3, would be a 3 by 2. Top row is first column, second row is second column now. And there you have it. So, that's kind of neat, I guess. Let's look at this guy. Let's pick a matrix that's a square matrix. 3, 1, 4, 6. Let's look at A transpose here. That would be 3, 4, 1, 6. What would happen if you added them together? Well, you would get 6, 5, 5, 12. Is that true? I believe so. And that is what we refer to as a symmetric matrix. Okay. Symmetric matrix is the idea that, well, let's just see if you can figure out what they're called. A transpose, A times A transpose is also a symmetric matrix. Again, if you start off with squares, and so does A transpose times A. Let's see what that would look like. If you took A times A transpose, you'd get 9 plus 16 is 25. And then you would get, yes, and so then you'd get 3 times 1 is 3, plus 4 is 27. And you get 1 times 3, plus 6 times 4 is 27. And then you'd get 37. And if I go the other direction, I have to do it like this. I can't visualize sometimes very good the other direction. So let's do 3 times 1 is 3, plus 1 is 10. 3 times 4 is 12, plus 6 is 18. 4 times 3 is 12, plus 6 is 18. And 4 is 16, plus 36 is 52. So what you have here are what are referred to as symmetric matrices. Symmetric matrices means it doesn't really matter what's on this diagonal. Whatever's on the opposites of the diagonals will be the same. Those make them symmetric matrices. We'll come back to that a little bit later on. I mean, that will pop up from time to time. Just be aware of that. Okay. couple other properties of the transpose besides that. So A transpose and then transpose that. Obviously, you get back to A. K A transpose is the same as saying K times A transpose. Same thing. Think about that. All you're doing is this. You're multiplying by the scalar first and then taking the transpose of that, or do the transpose first and then multiply by a scalar. Same thing. So if you have A to the R, that is, you have A to the R, A matrix times A matrix times A matrix. Obviously, A has to be a square matrix to pull that off, because you can't take a 3 by 2 times a 3 by 2, right? That won't work. The only way this is going to happen is if you have a square matrix. So, for instance, a 2 by 2 times a 2 by 2 will give you a 2 by 2, which then you could multiply by another 2 by 2, and you could keep going. So we're saying that this, obviously, A has to be a square matrix. So you could raise it to the R power and then take the transpose, or you take the transpose first and then raise it to the R power. You'll get the same answer. Okay? This is true for non-negative R's. Okay? A plus B transpose is the same as saying A transpose plus B transpose. I think that's pretty straightforward. Clearly, you're just adding up the pieces of the matrix. You see a new matrix and then flopping them around, but you could have just flopped them first and then added them. And then this one here is the one that's a little weird. AB transpose is the same as B transpose A transpose. What? Let's try that one, shall we? So to pull that off, I think I want to make sure I start with a square matrix. I think it will not work with a non-square matrix. So this is A, let's say, and this is B. That's cool. 3, 1, 4, 1, 9. Nice. So AB is going to be 6, and 12 is 18. And then it's going to be 2, and 27 is 29. And then we're going to have 3 and 0, so 3, and you're going to have 1 and 0, which is 1. Cool. So that is AB. And so if you take AB transpose, you're going to get 18, 29, 3, 1. It's AB transpose. Now let's take B transpose. So that would be 3, 4, 1, 9 times 2, 1, 3, 0. And so that's 6 and 12. That's 6 and 12 is 18, you moron. There you go. And then you have 3 and 0 is 3. And then you're going to have 1, that's going to be 2, and 27 is 29. And you're going to have 1 and 0, which is 1. Check it, it's the same. Okay? But again, that won't work if they're not square matrices. So section 3.2 is just, here's some algebra. Isn't that cute? That's nice. And that's wonderful and all. Great, good for us. And then you're just going to be using that in section 3.2. I think we talked a little bit about some of that last week. Now, the inverse of a matrix. That's where this gets kind of fun. And I've used it a couple of times in class, just so we're clear. So the A, your book uses A inverse like that is equal I, or IA. So A inverse is also equal to I. Now, I personally like writing my inverses like that, but you do you. I'll probably end up writing them both ways. Okay, so meaning that if I start with this, for instance, if I did an inverse function, this is saying that I take an A matrix times its inverse. The only way for that to happen is if A is square. So A must be square. Now, the biggest reason, of course, is because obviously you have to be able to multiply them, and I have to be able to multiply them both directions, which means they have to have the same dimension, obviously. So that's obviously true. Of course, A inverse will also be square then. Okay, number one. There's another reason for that, is because, and I'll show you later on when we solve these, the systems of equations using the inverse matrix. The only way you can solve an equation is if you have, like, for instance, 3 equations with 3 unknowns. In other words, it has to be square to pull that off. Okay? So kind of cool, kind of fun almost, I think you'll find. Okay? So A does not always have an inverse. Okay, A does not always have an inverse. But when he does, we say A is invertible. Okay? One, for instance, situation where it will not have an inverse is it would be a situation like this. Okay? Where the top and the bottom are multiples of one another. In the case of a 2 by 2, we would say that these guys are linearly dependent. Or in the case of a 3 by 3, in the case of a 3 by 3, this guy here is a linear combination of these guys. It also would not have an inverse. Okay? So it's going to come back down to independence again. If these functions are independent, if these lines are, if these rows are linearly independent, which they're not, if they are, the function will have the matrix will have an inverse. If they're dependent, or if you prefer to say they are linear combinations of one another, then they will not have an inverse. They're not invertible. Okay, so just be aware of that. It's pretty straightforward. Just be aware of that. So if A is an invertible matrix, and we talked about this before, so A times X equals B. Okay, we did this, and actually your book uses little b here to remind us that that's a vector. This is a matrix. This is also a vector. So think about that. Let's say A was n by n. And then if I look at this thing here, then that means that B is an n by 1. Or not X, I mean. And also B is also then going to be an n by 1 matrix. Okay, so in a situation like this, like that, we would have this matrix equation. And I've shown you this before. So what I need to find is this is A, this is X, and this is B. What I need to do is I need to solve for X. To solve for X, I need to multiply by A inverse on this side. And if I do it on this side, I must do it on this side as well. And this will give me the identity matrix times X, so in other words, just X, is equal to this guy right here. So in other words, if this guy is invertible, there will be a solution. It will be a unique solution as well. Okay? So in a case of a 2 by 2, and we'll come back to this one up here. In the case of a 2 by 2 matrix, the inverse is given by, if this is A, then A inverse is dA negative B negative C, and then times, oops, I didn't leave room for that. Just a minute. 1 over the determinant of A. Okay? So, and then the determinant of A, in the case of a 2 by 2, is just AD minus CB, or BC, if that makes you happy. Okay? So in the case of this one up here, we would end up with negative 1, 3, negative 2, negative 2. The determinant would be negative 3 minus 4 would be negative 7. So I'll do this times this. Let's see if this works. That's going to be negative 3 plus 4. Negative 3. Oh, yes. Negative 3 minus 4 is negative 7. Don't panic. It's going to be negative 2 plus 2 is 0. It's going to be negative 6 plus 6 is 0. It's going to be negative 4, negative 3. If you do that, well, obviously that's 1, 0, 0, 1. So x and y is all I'm left with is equal to. Now on this side here, you can multiply through by the fraction first, or weight. I'm going to weight, obviously, because it's going to be gross otherwise. Negative 7 minus 18 is negative 25. -2, and it says -14 plus 27 is 13. So when you multiply that through, your answer is 25/7 and -13/7. That would be your x and y. Okay, and we can do that for, again, any size matrix that we wanted to. Back in my day, before calculators could do it all for us, which was okay, but it was cool back in the day because this is how we did it. We thought we were so cool. We solved equations super fast using matrices. They're pretty cool things. Whatever. Obviously, if you take the inverse of an inverse, what do you get? Obviously, you get back where you started from. Just a couple more properties here. Oops. And we will use a couple of those properties later on, just so you know they're there. Couple more. Obviously, A transpose, and then if you're taking a transpose and then an inverse, again, A better be a square matrix, and here A and B better be squares. Okay. Anytime, anywhere you're taking an inverse, the matrix would better be square. Obviously, you can take the inverse and then transpose it, or take the transpose first and take the inverse. You get the same answer. And then same deal as before. You can flip-flop those. Again, non-negative integers for n. Pull that off. Just nice. Okay. Yeah. So those are just like some concepts that you're gonna do. And so what we're going to do is then talk about, well, how can we get to a matrix? How can we get to an inverse of anything other than a 2x2? And that's a good question. Okay, so we are going to just talk about how to pull that off, and we're going to use some Gauss-Jordan elimination to do that. And then we're going to come back and talk about some other different ways of going about it. Okay, so there's a couple other things I'm going to skip over, and then I'm going to come back to them. I just think this one's kind of fun. So if you take an inverse of any square matrix, this works for any square matrix. You can even do it with a 2x2. What you're going to want to do is you're going to start off with your matrix. I'm just making these up. And then you're going to augment the same size identity matrix. Okay? The game is this. You are going to do elimination on this side. You are going to end up with this on this side. When you get this on this side, whatever's left over here, this is A inverse, where this is A. Okay? So, Gauss-Jordan elimination. What you're left with over here is the inverse of A. So let's go see if we can play that game and see what we get here. So, oh, that's gross. Okay, so to get that there, I'm going to take 2r1 minus r2, I guess. So, it's going to give us 6. Minus 6 is 0. 0, it's going to give me 4, plus 1 is 5, it's going to give me 10, minus 6 is 4, and it's going to give me 2, and it's going to give me -1 and 0. Okay? And then, let's do this. Let's take 2r1 plus 3r3. That's going to give me 6, minus 6 is 0, obviously. 4 plus 3 is 7. 10 plus 27 is 37. It's 2. That is 3, and that's 0, of course. Nice. Now, I need zeros here and here, so I'm going to take 5r1 minus 2R2. So it's going to give me 15 minus 0 is 15. It's going to give me 10 minus 10 is 0. It's going to give me 25 minus 8 is 17. It's going to give me 5 minus 4 is 1. It's going to give me 0 plus 2 and 0. Nice. And then I want to get rid of this fella, so I'm going to do 7R2s minus 5R3s. And so middle is not changing this time. And then I'm going to do 0, and then it's going to be 0, and then it's going to be 28. Oh, jeez, what kind of idiot chose this problem? So 28 minus 37 times 5. Negative 157. And then it's going to be 14 minus 10 is 4. And it's going to be negative 7. And then it's going to be negative 15. Okay. It's at this juncture you could divide everything over here by negative 157. Ugh. Fractions, though. I don't think I want to do that. So 17 doesn't go into 157, does it? I don't think so. Nope. Sorry. Well, great. So we'll do 157 times R1 minus 17 R3s, I guess. Plus 17 R3s. Cool. So 157 times 15 is 2355. 0, 0. What a mess. So 157 times 1 plus 17 times 4 is 225. And then we're going to do 157 times 2 plus 17 times negative 7, 195. And then 17 times 15, I should know that, but I don't tonight. 255, so negative 255. Cool. All right, middle row, gross. I'm going to take 4, so 157 R2 plus 4 R3. Gross. Middle one. 157 times 5. 785. This better be 0. That was the whole point of doing it. 157 times 2 plus 16 is 330. Negative 157 minus 28. Negative 185. And then negative 60. Okay, so then if a fella were to divide this out, one would get da-da-da-da. And then let's divide the math here. 225 divided by 2355 is 0.0095. 0095. Don't I want to do that? No, I don't want to do that. I want to do 45 over 4711. Is that what I said? Oh, I got an extra 5 in there. That's my problem. 15 over 157. That's more better. 15 over 157. And 195. 13 over 157. And then 255 17 over 157. If you're starting to see a pattern, that's right. 666. Ooh. Ooh. Wait, what just happened? Oh, darn it. $66 over 157. And then negative 185 divided by 785. Negative 37 over 157. And negative 60 divided by 785 is negative 12 over 157. It's so weird. It's almost like 157 is a big deal here, friends. So in other words, that right there is my inverse matrix. And I could write it like this. And so it turns out that's kind of a big deal. So what I'm going to do is I'm going to find the determinant of my original matrix. So first thing I'm going to do is input my original matrix into here. Oops. Cool. And then what I'm going to do is second math matrix. Okay, and I'm going to find the determinant first. Nuh-uh. Now no way. Now no way. So if I pulled this guy out, darn it. What you end up with is this. And so it turns out that one way to find, or every time you have an inverse, it'll always be 1 over the determinant times a new matrix piece. Always, 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 always. Take it to the bank. Now, I can check myself that this is the right, I can do it a couple of ways. But I'm going to do it this way. To prove that I'm correct here, I am going to type in my new matrix. And by the way, I could have left the negatives inside. It wouldn't have mattered at all. I just wanted to show the point of that. Boom! And bam, friends, right there, we have got ourselves the identity, which means that we did it correctly. That is a big deal, okay? And yes, obviously there's calculators. The 89 will find the inverse. That's true. But to understand how to get there, what you're really doing, going all the way through, all doing the Gauss-Jordan elimination, is you're doing it so that you're solving the equation. You're building in all the steps that you would have needed to solve the equation, so that when you do the multiplication, you get right down to the zeros, okay? So that's in essence what you're doing. You're building it into the inverse so that when you multiply them, all you're doing is putting the last little piece together, and bam, you get down to the matrix equivalent of 1. That is the identity matrix. Okay. So another little definition here is the idea of an elementary matrix. So I'm just going to read the definition here. It's a matrix that can be obtained by performing elementary row operations on an identity matrix. Okay, so it's any matrix that can be made or formed, obtained. What does that say? Obtained by performing elementary, that means adding, subtracting, multiplying, row operations on an identity. Okay, so when you think about that, does it have to be a square matrix? No. The only way that it wouldn't be a square matrix is if you multiplied it. So for instance, if you had this guy here, which you can't do, stupid. Try again. There you go. This is an elementary matrix. It's an elementary matrix because you multiplied by that. But that's one of the only ones where that will happen. And so that's but the main ones are going to be stuff like this. So for instance, 1 0 0 0 0 or 0 1 0, sorry. 0 0 1. Suppose I did 3R1 plus R2 and wrote the answer right on the top row. That'd be 3 plus 1 and then 0. And then let's say I did in the middle row, I took R2 plus 4R3 minus R1 because I feel like it. So row 2, so 0 plus 0 minus 1. So it's 1 plus 0 minus 0 is 1, and then it's going to be 0 plus 4 minus 0 is 4. And then let's just say I did 5R3. Sure, why not? 0 0 5. Okay, that right there is an elementary matrix, for instance. Interestingly enough, if a guy wanted to build a test for people and they wanted to have problems on there they know that worked, that in other words, that they that I could always get back to an identity matrix, is you could start with an identity and then blow it out from there. And so it it is what it is. It's not too bad. Now, so it says this: let E be an elementary. So yeah, so E is an elementary matrix. Elementary matrix, and it is an n by n. And if the same row operation is performed on an n by r matrix, so an n by r, so if you had an n by r matrix A, and you did the exact same row operations on this guy, okay, the result would be the same as taking E times A. Okay, so let's try that. So let's just do a nice 2 by 2. It's Sunday night. I don't want to work that hard. Or Saturday night. What am I saying? 7R1 plus R2. And 3R1 plus 6R2. Sure. And that gives us 7 and 0 and... No, 7 and 1, sorry. 7 and 1. And then it gives me 3 and 6. Cool. Now, let's take some other matrix A. Let's say it is a n by r. Let's go big. Oops. An n by r. So again, it's going to be a 2 by, and let's do a 2 by 4 this time, shall we? No, I don't like negatives. Let's get rid of the negatives. So what I need to do is 7R1 plus R2. So it's going to be 7 plus, that is 6, 13. That's 21. That's 20. That's 21. That's 19. That's 14. And 4 is 18. Bottom row, I had 3R1 plus 6R2. So that's 3 and 36 is 39. That's 9 minus 6 is 3. That's 9 minus 12 is negative 3. That is 6 plus 24 is 30. Cool. Cool. Nice. Nice. So now focus on this carefully. Okay, what it said is the following. It says show that the result is the same as taking E times A. So E, remember E was, where's our E at? E is this guy right here is our E value. Okay, if I were to multiply that by my A, what would I get? So it's 7 and 1 and 3 and 6, right? And then it's 1, 3, 3, 2, 6, -1, -2, and 4. Let's see what we get. We get a 2 by 2 times a 2 by 4. So I will clearly get a 2 by 4 when I'm done. So it's 7 and 6 is 13. That's 21, and -1 is 20. That's 21, and -2 is 18. That's 14 and 4 is 18, and then that's 39, and then it's 9 minus 6 is 3, and then it's 9 minus 12 is -3, and then it's 6 plus 4 is 30. No way. Isn't that cool? Where will that come into play? I'm glad you asked, friend. I'm glad you asked. Because to me, when I was a kid, that didn't really make that much sense to me. But wait. What are you doing when you do this thing right here? And you go from whatever A is. What are you doing? You are doing, this is your E that you're creating. Are you with me? This is the E that you're creating. This E right here, you're doing the same elementary row operations on this guy that you're doing on this guy. Does that make sense? You're doing the exact same ones that you're getting there. Okay? So what we're going to end up with, right, is the idea that if I take then EA, right, whatever I do, so I'm going to take this E right here times the A, what do you end up with? Well, we ended up with whatever we got when we did the elementary row operations on here, which was what? This guy. So what does that say about E? That says that our E is A inverse. Make sense? Now I cannot, when some people, and I'm not one of them, can read the text and they come to this like 3 or 4 pages before the algorithm for finding inverses. Okay? And they're like, oh, well, sure, that makes perfect sense. Well, not this kid, friend. Not this kid. It didn't make sense to me when I was a kid. And it honestly, first couple times I taught this class, it's kind of like, yeah. I remember this algorithm. I had to really sit there and scratch my head on it, you know. But the idea is that you are starting with A. You did elementary row operations to end up with the inverse, and then you ended up with an E on this side. Okay? Well, what we said is that this answer here will be equal to the same as taking E times A. And that's what we did. So what does that say? Well, if you end up with the identity, that means the E has to be the inverse matrix. That is why that works. If that weren't true, no bueno. You could not solve that thing. Okay? So I'm going to do one example of like a solving problem here, and then I think we'll just call it a night. I'm just going to, again, I like to keep everything to be more or less applicable. And obviously I could solve this in 5 minutes with my calculator, so I'm not going to make a big deal about it. It's not like that. I don't want you to be, you know, oh, yeah, well, why are we wasting our time? That's, you know, no. I want you to learn. I want you to feel comfortable about what you're learning, but I like applications always. Write down my answer here so I know what I'm trying to shoot for. So, let's see. If we do 3, 6, and then 4x minus y plus 3z is -1, and then x plus 4y minus z is 10. Cool. So if I were to solve this, what I'm looking for is this guy here, 3, 2, 1, 4, negative 1, 3, 1, 4, negative 1 times x, y, z equals 6, negative 1, and 10. So let's go and find ourselves the inverse matrix for this guy. And let's augment it. So whatever we're doing to the one side, we're doing to the other side as well. We're creating this elementary matrix. You'd think I'd be smarter about this, but I really am not. 4r1 minus 3r2, and little r1 minus 3r3. So that's going to give me 12 minus 12 is 0, obviously. Zero, and then it's going to give me 8 plus 3 is 11. Give me 4 minus 9 is negative 5. And then it's going to give me 4, and it's going to give me negative 3, and it's going to give me 0. Then I'm going to take r1 minus 3r3 is going to be 0. It's going to be 2 minus 12 is negative 10. It's going to be 1 plus 3 is 4. It's going to be 1, and it's going to be 0, and it's going to be negative 3. Cool. Now, need to get the zeros here and here. So let's do a little 11r1 minus 2r2. And so it's going to give me 33 rather. It's going to give me 0, and it's going to give me 11 plus 10 is 21. 11 minus 4 is 3, minus 8 is 3, and then it's going to give me 6, and it's going to give me 0. Middle one didn't change. And then the bottom one, I'm going to do, I don't know what I'm going to do, 10r2 plus 11r3s. So 0, 0, it's going to be negative 50 plus 44 is negative 6. It's going to be 40 plus 11 is 51. It's going to be negative 30. It's going to be negative 33. Okay? It's up to you. If you want to divide 3 by 6 right now, go for it. Otherwise, just keep trucking. It's going to be 6r1 plus 21r3. And it's going to be 6 rather, r2 minus 5r3. So on the top row, it's going to be 6 times 33 is, I don't remember, it's late, 198. And then it's going to be plus 21 times 11, 231. And then it's, oh no, it's not either, you dumb jackwagon. And then it's going to be 6 times 21, which is 126, minus 126 is 0. Good night, nurse. That's going to be 18. Oh, I can't do this math in my head anymore. Goodness. 18 plus 21 times 51 is 1,089. And then it's going to be, good night, 36 minus 30 times 21, negative 594. Makes my bracket a little bigger, I guess. And then it's going to be 21 times 33, negative 693. Middle row, oh, the bottom row doesn't change. Cool. And then middle row there, so I'm going to do, I already did it, so it's going to be 0, it's going to be 66, it's going to be 0, and then it's going to be 6 times 4 is 24, minus 5 times 51, negative 231, and it's going to be negative 18, plus 150. 132, And then it's going to be 5 times 33, 165, right? 165. All right. Awesome. Let's see what we get here, shall we? So let's go ahead and divide. So 11 halves. Oops. 594. 3. Now, sometimes you're thinking, well, I thought you said it was going to always have the same denominator. Well, there's going to be common denominator issues sometimes where it's not going to be so obvious. But like 7 halves, you know, you can't say, like on this next one here, you're going to see another whole number with a 2 on that one. So 7 halves. But 132 divided by 66 is just 2. And then 165 divided by 66 is 5 halves. So one could see so far you could all make them all out of 2, right? And so it would work that way. 51 divided by 6 is negative 17 halves. And 5 and 5.5, right? So would that be 33/5? What? What just happened? Oh, because you divided by 5, you jackwagon. 11 halves. That makes more sense. All right. So anyway, my point is this should all be, and so you could all write them as all over 2. Okay. Now, supposedly that is my inverse function. So I'm just going to write that down. Actually, I'm going to input that in my calculator. And I'm just going to leave. I'm not going to try to factor anything out. I'm just going to go 11 halves, comma, 3, comma, 7 halves, bracket, or semicolon rather, negative 7 halves, comma, 2, comma, 5 halves, negative 17 halves, comma, 5, comma, 11 halves, times, and then remember times my original function, which was right there. What? What did you do, Jay? Oh. Uh-oh. So what that means is somewhere along the line, Jay made a little bobo. Great. Darn it. I'm going to pause you for just a minute. All right, so I dropped a negative here and here. So let's try this right here. Let's go back and fix those. So it should have been a negative 3 and a negative 7 halves. Fart. Still messed up. Okay, I'm just a moron. Do you see right there? It clearly says 7:20 seconds. Do you see that? What an idiot. All right, let's see if I can get it typed in correctly this time. Give it to me. Well, hallelujah, it actually worked. So what I need to do then is clear this, grab this guy here, lose this, because I was just confirming that I had the actual correct inverse matrix, and then put times, and then I'm going to try something a little different here for you. I hate having to type in something, comma, semicolon, comma, you know, whatever. It's annoying. So what I'm going to do instead is I'm going to put this in, and then I'm going to use a, so I'm just going to go 6, comma, negative 1, comma, 10. But what I'm going to do is I'm going to take the transpose of that matrix. So I typed it in as a row vector. Now I'm making it a column vector and then just transpose it. And so there's the answer, 1, 2, -1. Yes, which is the correct answer. Hot dang, I feel good about my life now. Not really, but kind of. All right, so that is sections 3.2 and 3.3. I'll make a separate video for 3.4 tomorrow.